One of the main reasons why the discrete Fourier transform is a popular tool for image processing is the convolution theorem. This result says that instead of having a convolution performed in the space domain, as we have seen in the lecture about filtering in the space domain, we can instead perform a dot-wise or a point-wise product in the Fourier domain. By taking the Fourier transforms of f and h and having capital F and capital H, instead of performing a very complex in terms of running time convolution, it is just a mere product, and therefore is a linear procedure, because it just requires one product per point in the image. And then we take the inverse of the Fourier transform and have the result, as a result, the image, a new image processed. So this is the basic idea. If we have a Fourier transform of an image f and the filter h, then we make a product between them, take the inverse transform, and then we have the image processed here. The algorithm to do that is works like that. So we recommend it, and if you have an input image f of x and y with size m times n, to instead of use the actual image to perform the convolution, the Fourier transform, we use a padded version of this image. How that works? So we have seen in the filtering case that if we don't pad the image, we are not able to compute values on the border of the image. So what we do first is to obtain optimal values to perform this transform, P and Q. I'm going to show you two options. The first one is to use the next power of 2, which can lead us to a large value. So instead we can use P as the double of the size of n and Q as the double of the size of m. Then we create an image fp, in which here P is a padded version of the image of size P times Q, padding the remaining pixels with zeros. And then we compute the Fourier transform of this padded image. We also have to compute the Fourier transform of a filter h. So if the filter h is also in the space domain, we must do the same. So pad the filter with zeros until it has the same size of the image, and then compute the Fourier transform. In the Fourier domain, we are going to take the product between f and h, and then take the inverse, and it is recommended to take just the real part of the inverse in order to avoid numerical approximation errors. And then, because this first image is actually an image with size P times Q, we must crop the image again to the size n times n, removing the zero padded region and obtaining an image that has the same size of the input one. As in the space domain, we also have typical filters in the frequency domain. The first one that I'm going to show you is the low pass filter. It allows the low frequencies to pass or to be kept in the image, so retaining just values that are related to smooth transitions. So I'm sorry, here there is retaining higher frequencies, retaining lower frequencies, and removing higher frequencies, okay? So this is just an error here in the slide. So it will retain the low frequencies while discarding the higher ones. Remember, in here I'm considering the FFT shift version of the Fourier domain. So in the central part I have low frequencies, and far from the center higher frequencies. So see that we use a circle here. This is because we are maintaining all the low frequencies in a symmetrical way. But we can also design filters that has other shapes. By using a circle, we have what we call an ideal filter, because we remove all frequencies beyond some given threshold. On the other hand, we can also perform a high-pass filter, or design a high-pass filter. High-pass filter remove the lower frequencies, so it's the opposite of it. So we remove everything that's inside this circle, this black circle, and keep the remaining frequencies on the white that are related to the white values here. So black pixels in this case are 0 and white pixels are 1. So we just, when we make the product, we just keep everything that's high frequency. Similarly, an ideal high-pass filter removes all frequencies below some given threshold. So this means that we use a circle as a pattern for this frequency, this filter. A bandpass filter selects a range of frequencies to be kept while removing all other ones. So in this case here, I'm using a ring to define all frequencies at UV that I want to keep, while discarding lower and higher frequencies when compared to that. And on the other hand, I also have the band stop filter, which will remove just some band, so in between some given thresholds, so a pair of thresholds here in this case. So it will remove everything that lies inside this ring here, while keeping lower frequencies and higher frequencies. Let me show you a few examples to illustrate that. So we have this image here on the left hand side, and by taking its Fourier transform and multiplying with this filter on the middle, which is a low pass filter, a high pass filter, because it removes the central region here of the Fourier transform, what we have is this image on the right hand side. Note that it remains just the transitions. So everything that's related to higher frequencies are abrupt transitions. So I'm going to keep transitions, abrupt transitions especially, and I'm going to lose the meaning, for example, of flat regions, of color. Everything is lost because we lost that by removing the central part. Note that the more abrupt the transition is, the higher the value of this the resulting image. So this is visible in this part here, because the white circle in here is more similar to the background. There's a light gray value. It has in the high pass filtered version, it's smoother because the transition was already a smooth in the beginning, in the original image, while for black to gray it enhances much more. The low pass filter behaves in the opposite way. So by removing the higher frequencies, instead of losing the flat regions, we are going to lose the transitions. So any transition below some given threshold is going to be lost. So in here I don't see anymore, cannot see anymore the transitions between those horizontal lines, and now what I can see is a rectangle. But because the circle was wide enough, I kept the transitions between those those horizontal lines, which are a little bit more further from each other. This first square here, the smaller one, becomes a circle because I lost the information on the corners. So what I'm doing basically is to remove very fine transitions and keeping the other ones. And finally, an example of a band stop filter, which is used to remove usually to remove interference in a given frequency value. So I have this image of a bird, and this is the Fourier spectrum of the image. And if I, for example, insert some interference, so this is a regular pattern that is interfering with the image, the other image now has a new values of frequencies that are spread along this diagonal. By designing a very rough an estimate of this frequency region here, so I'm keeping the central part of the Fourier transform, but removing values lying in these regions here, in these black regions here. What I have is this image. So it is not perfect, but as you can see, it removes frequencies. It stops frequencies that were interfering abruptly with the image, and then makes it a little bit more smooth. So in this way, we can design filters directly in the frequency domain, which can be very useful for image processing.